Mercury, the closest planet to our Sun and the smallest in the solar system, remains one of the least understood celestial bodies. While planets like Mars, Jupiter, and Saturn often steal the spotlight, Mercury has received far less attention from scientific study missions. Initially perceived as a cold, dead, and cratered world akin to Earth's moon, recent discoveries have unveiled surprising secrets hidden within its enigmatic surface. Mercury, known as the innermost planet of our solar system, has fascinated civilizations for millennia. Dating back to Sumerian times 5,000 years ago, it was observed by ancient cultures and named differently across civilizations. In classical Greece, it was known as Apollo when appearing as a morning star just before sunrise, and as Hermes when seen as an evening star just after sunset. Its rapid movements across the sky earned it the name Mercury, after the swift messenger of the gods. For centuries, Mercury remained a mystery, challenging astronomers due to its proximity to the Sun and elusive visibility. It wasn't until the mid-20th century that significant strides were made in understanding this planet. The discovery of its true rotation period and detailed surface mapping became possible thanks to NASA's Messenger probe, launched in 2004, which orbited Mercury from 2011 until its planned crash in 2015. Messenger's findings revolutionized our understanding of Mercury's geological history and confirmed predictions from Einstein's theory of relativity. Mercury's unique characteristics set it apart from other planets. Despite its small size, its density is remarkably high, primarily due to its large metallic core, which occupies about 61% of its volume. This core structure, unlike any other in the solar system, contributes to Mercury's extreme temperature variations, ranging from scorching hot to bitterly cold. Join us as we delve deeper into Mercury's enduring mysteries, exploring its hidden secrets and the implications they hold for our understanding of planetary science and beyond. Its nearness to the horizon also means that Mercury is always seen through more of Earth's turbulent atmosphere, which blurs the view. Even above the atmosphere, orbiting observatories such as the Hubble Space Telescope are restricted by the high sensitivity of their instruments from pointing as close to the Sun as would be required for observing Mercury. Because Mercury's orbit lies within Earth's, it occasionally passes directly between Earth and the Sun. This event, in which the planet can be observed telescopically or by spacecraft instruments as a small black dot crossing the bright solar disk, is called a transit-sea eclipse, and it occurs about a dozen times in a century. The next transit of Mercury will occur in 2019. Mercury also presents difficulties to study by space probe because the planet is located deep in the Sun's gravity field. A great deal of energy is needed to shape the trajectory of a spacecraft to get it from Earth's orbit to Mercury's in such a way that it can go into orbit around the planet or land on it. The first spacecraft to visit Mercury, Mariner 10, was in orbit around the Sun when it made 3 brief flybys of the planet in 1974-1975. In developing subsequent missions to Mercury, such as the U.S. Messenger spacecraft launched in 2004, spaceflight engineers calculated complex routes making use of gravity assist from repeated flybys of Venus and Mercury over the course of several years. In the Messenger mission design, after conducting observations from moderate distances during planetary flybys in 2008 and 2009, the spacecraft entered into an elongated orbit around Mercury for close-up investigations in 2011. In addition, the extreme heat not only from the Sun, but also radiated from Mercury itself challenged spacecraft designers to keep instruments cool enough to operate. Scientific knowledge about Mercury was greatly increased by Mercury flybys. For instance, a completely unexpected discovery made by Mariner 10 was that Mercury possessed a magnetic field. Planets theoretically generate magnetic fields only if they spin quickly and possess a molten core. But Mercury takes 59 days to rotate and is so small, just roughly 13 Earth size, that its core should have cooled off long ago. An unusual interior could help to explain the differences in Mercury's magnetic field when compared to Earth. Observations from Messenger revealed that the planet's magnetic field is approximately 3 times stronger in its northern hemisphere than in its southern. Scientists suggest that Mercury's iron core may be turning from liquid to solid at the core's outer boundary, rather than the inner. In the words of Christopher Russell, a professor at the University of California, Los Angeles, who co-authored that model, "It's like a snowstorm in which the snow formed at the top of the cloud and middle of the cloud and the bottom of the cloud too." Our study of Mercury's magnetic field indicates iron is snowing throughout this fluid that is powering Mercury's magnetic field. The atmospheric gases tend to accumulate on Mercury's night side, but are dissipated by the brilliant morning sunlight. Many atoms in Mercury's surface rocks and in its tenuous atmosphere become ionized when struck by energetic particles in the solar wind and in Mercury's magnetosphere. Unlike Mariner 10, the Messenger spacecraft had instruments that could measure ions. During Messenger's first flyby of Mercury in 2008, many ions were identified, including those of oxygen, sodium, magnesium, potassium, calcium, and sulfur. In addition, another instrument mapped Mercury's long, comet-like tail, which is prominently visible in the spectral emission lines of sodium. Although the measured abundances of sodium and potassium are extremely low, from hundreds to a few tens of thousands of atoms per cubic centimeter near the surface, telescopic spectral instruments are very sensitive to these two elements. Astronomers can watch thicker patches of these gases move across Mercury's disk and through its neighborhood in space. Where these gases come from and go was primarily of theoretical rather than practical importance until the early 1990s. At that time, Earth-based radar made the remarkable discovery of patches of highly radar-reflective materials at the poles. Messenger later observed that the patches were made of water ice. Despite Mercury's proximity to the Sun, the water ice was able to survive by being covered in an insulating layer of dark organic material in permanently shadowed regions of deep near-polar craters. The idea that the planet nearest the Sun might harbor significant deposits of water ice originally seemed bizarre. However, Mercury has accumulated water over its history, most likely from impacting comets and asteroids. Water ice on Mercury's broiling surface will immediately turn to vapor, and the individual water molecules will hop in random directions along ballistic trajectories. The odds are very poor that a water molecule will strike another atom in Mercury's atmosphere, although there is some chance that it will be dissociated by the bright sunlight. Calculations suggest that after many hops, perhaps 1 out of 10 water molecules eventually lands in a deep polar depression. Because Mercury's rotational axis is essentially perpendicular to the plane of its orbit, sunlight is always nearly horizontal at the poles. Under such conditions, the bottoms of deep depressions remain in permanent shadow and provide cold traps that hold water molecules for millions or billions of years. Gradually, a polar ice deposit builds up. The susceptibility of the ice to subliming away slowly is reduced because it is cloaked by an insulating debris layer, or regolith, about 10 to 20 cm thick made of organic compounds that also arrived on Mercury in cometary and asteroidal impacts. Another significant feature, Mercury speeds around the Sun every 88 Earth days, traveling through space at nearly 180,000 km/h, faster than any other planet. Its oval-shaped orbit is highly elliptical, taking Mercury as close as 47 million km and as far as 70 million km from the Sun. If one could stand on Mercury when it is nearest to the Sun, it would appear more than 3 times as large as it does when viewed from Earth. Oddly, due to Mercury's highly elliptical orbit and the 59 Earth days or so it takes to rotate on its axis, when on the scorching surface of the planet, the Sun appears to rise briefly, set, and rise again before it travels westward across the sky. At sunset, the Sun appears to set, rise again briefly, and then set again. In 2016, a rare transit of Mercury happened where the planet crossed the face of the Sun as seen from Earth. Mercury's transit may have yielded secrets about its thin atmosphere, assisted in the hunt for worlds around other stars, and helped NASA hone some of its instruments. As Mercury takes just 88 Earth days to orbit the Sun, and Earth takes approximately 365 days, approximately 3 or 4 times a year, Mercury overtakes Earth during its trip around the Sun, and an optical illusion occurs. Mercury appears to move backward across the sky for about 3 weeks. It is during this time Mercury is said to be in retrograde. Astrologers consider Mercury in retrograde to be a time of misfortune and miscommunication, as the perceived backward motion interferes with the planet's rules. The latest observations supplement those with scarps a few kilometers long and only tens of meters tall, and more importantly, geologically young. The larger scarps are ancient and softened by the passage of time, but the smaller ones are crisp and fresh, likely formed within the last tens of millions of years. This suggests that instead of being cold and dead, Mercury is still geologically active today. As its hot core cools, the planet shrinks and the surface crumples. But the story of Mercury gets stranger still. When mapping the geology of Mercury's surface, Messenger found distinct regions of unique geochemistry, a mix of terrains instead of a single, roughly similar surface. The spacecraft also spotted delicate volatiles like potassium and uranium chemicals that should have been destroyed by the enormous heat of a crust-shearing collision or the scorching heat of a boiling sun. By their very presence, these chemicals argued against either theory for Mercury's oddly large core, leaving scientists scrambling for a new theory. More data poured in from MESSENGER, with scientists identifying pyroclastic flows that could only be the result of explosive volcanism lava mixed with volatile gases like water and carbon dioxide. More chemicals scientists didn't expect in abundance on a planet so near the Sun. Soon after the spacecraft's radar spotted water ice lurking in the shadows of polar craters reminiscent of the ice hiding in polar craters of our Moon, the MESSENGER mission came to an end in 2015. The spacecraft running out of fuel and deliberately crashing into the planet. Now, scientists are left analyzing and reanalyzing the data from its 4-5 orbits to try to piece together a new explanation for how Mercury formed that pulls all these pieces together. But in all the mysteries lays a tantalizing new possibility, investigating this deceptively simple planet for quakes. If Mercury truly does have a hot liquid core and is geologically active today, every time the crust moves to create a new ridge or wrinkle, a quake releases seismic waves propagating through the planet. On Earth, we detect that seismic energy with seismometers, observing the speed and distribution of the waves to map the planet's interior. Astronauts did the same thing on a smaller scale during the Apollo missions, observing moonquakes to understand what was going on below the surface. Scientists are planning to apply the same trick on Mars, sending a seismometer on NASA's delayed InSight lander to peer into the interior of Mars. This same idea could work on Mercury, with observations of seismic waves pinning down the true size and structure of the core. Detecting if, like the Earth, it has a warm liquid outer core around a solid interior. And if we can do that, we'll be one step closer to understanding how Mercury formed, why it is the way it is today, and what to expect of other rocky planets around distant stars. Another long-awaited mission is BepiColombo, a joint mission of the European Space Agency and the Japan Aerospace Exploration Agency. It will be only the second and the most complex mission in history to orbit Mercury. Its two orbiters, the European Mercury Planetary Orbiter and the Japanese Mercury Magnetospheric Orbiter, carry a combined 16 scientific instruments that will help shed light on some perplexing questions about the scorched planet. Do its polar craters really harbor water ice? Where does Mercury's magnetic field come from? What are the strange hollows on its surface? The mission, launched on October 19, 2018, is expected to reach Mercury in 2025 after a complicated 7-year journey, which requires 9 flyby maneuvers, including 1 at Earth, 2 at Venus, and 6 at Mercury itself. These flybys slow down the spacecraft against the gravitational pull of the Sun so that it can safely enter orbit around the innermost planet of the solar system. During the epic journey, the two orbiters travel stacked on top of an ESA-built Mercury transfer module. The module, with its 15-meter solar arrays, supplies power during the interplanetary cruise. It is also fitted with 3 selfie cameras, originally used to monitor the deployment of the solar arrays and antennas after launch, but these cameras are regularly being used by the BepiColombo team to obtain simple black and white images of the spacecraft's whereabouts. Thanks to these cameras, BepiColombo is sending regular postcards home from its encounters with various planets during the flybys. In April 2020, the spacecraft waved goodbye to Earth during a flyby at a distance of 12,700 km. In October 2020 and August 2021, BepiColombo flew past Venus. The first flyby saw the spacecraft zip by at a distance of 10,200 km from Venus. However, the second took it incredibly close, only 550 kilometers above the hot, cloudy planet's surface. This enabled scientists to take some unique measurements of Venus's murky atmosphere. Once the stacked spacecraft reaches its destination, the MTM will separate from the orbiters. Then, the two spacecraft will each be put in separate orbits to perform scientific investigations of Mercury. Japan's MMO will have an orbit of 9-3 hours and Europe's MPO an orbit of about 2-3 hours. The mission is expected to last for 1 Earth year, an equivalent of 4 Mercury years. It may be extended for an additional Earth year if funding allows and the two spacecraft remain in good health. Elsewhere, scientists also expect our most powerful space observation to take some photos of Mercury. James Webb is made up of a 6.5-meter gold-plated mirror, a sun shield the size of a tennis court, and an array of complex instruments that are cooled to temperatures only a few degrees above absolute zero. These features allow the telescope to observe the heavens in infrared radiation, revealing details of the universe just after its Big Bang birth 13.8 billion years ago and images of stars being born in dust clouds. However, the telescope is providing science with a further gift. Infrared radiation also turns out to be ideal for studying extrasolar planets or exoplanets, as worlds that orbit other stars are known. But how can Webb analyze exoplanet atmospheres? We all know that measuring a planet's atmosphere from hundreds or thousands of light years away is not as daunting as it may sound, though it certainly requires specialized instruments and rigorous techniques. One method is known as transmission spectroscopy. Here's how it works. Webb will first observe the star itself to obtain its spectrum. Next, Webb will wait until the exoplanet passes in front of its star and then measure another spectrum. At this point, the exoplanet will be backlit, which means the light of the star filters through the planet's atmosphere toward Webb. The planet's atmosphere will absorb some of that starlight, which will appear as dips in the spectrum. When researchers subtract the spectrum of the star from the combined spectrum of the star and the exoplanet, they are able to isolate which light was absorbed when it passed through the exoplanet's atmosphere. Next, they will compare the light absorption dips with extensive references that detail the light absorption of every molecule we've witnessed on Earth to determine which molecules are present in the exoplanet's atmosphere. An early target for astronomers using the James Webb has been TRAPPIST-1, a small cool star of a type known as a red dwarf 40 light-years from Earth. It has a family of 7 small rocky worlds, 3 of them lying within a region known as the habitable zone, where conditions are not too hot and not too cold to prevent water from existing as a liquid, a prime requirement for life to flourish, say astrobiologists. However, analyzers using the James Webb of 2 of the star's innermost planets, TRAPPIST-1b and TRAPPIST-1c, have revealed they possess either no atmosphere or only a very thin one. Further Webb studies of the rest of the system are now being planned. TRAPPIST-1's system still looks promising if you are seeking a world that might support life, said astronomer Dr. Joe Barrow of the Open University. However, one special problem does affect studies of stars like TRAPPIST-1. Red dwarfs are spotty. This may not sound like a terminal condition, but it does have serious implications. As Barrow said, our own sun has sunspots that are associated with intense solar activity, but it has relatively few. By contrast, TRAPPIST-1 has dozens of spots that change all the time, and that makes it very difficult to differentiate between these and features of a planet's atmosphere. The TRAPPIST-1 system is not going to give up its secrets easily. Ultimately, astronomers using the Webb telescope to seek out signs of extraterrestrial life are looking for a set of biological markers known as the Big Four: oxygen, carbon dioxide, water, and methane. Their presence in the atmosphere of an exoplanet would be a strong sign that life of some kind exists there. The life of the James Webb Space Telescope promises to be an intriguing and lengthy one. James Webb's flight on an Ariane 5 rocket from the European Space Agency's launch pad in Kourou, French Guiana, to its current position in orbit around the Sun was near flawless. The observatory used very little fuel to maneuver itself into its exact target location, and that means there will be extra to allow the telescope to orient itself for far longer than anticipated. Space engineers have calculated Webb's expected 10-year lifetime could be doubled in many ways. That is very good news. We will be able to do a lot more science with it. It is tremendously exciting. And if one day astronomers announce they found an Earth analog among the stars, what's next? The implicit part of the question is whether we can travel to it and live there. But simply put, we can't. It's not like we can go there. There's no Enterprise we can use to warp over to the nearest Earth 2.0, and without faster-than-light travel, it would be a long trip. Even the fastest spaceship ever launched would take the better part of a millennium to get to the nearest star system, Proxima Centauri, which does actually host an Earth-sized planet that might be within our range of acceptability. Better pack a lunch. So many sci-fi movies tell us we need to evacuate Earth, that it's a trope. This idea is far more fiction than science. Though humanity increases its number by more than 70 million people every year, you'd need to launch 2,000 SpaceX Starships every day just to keep up with that increase. Even ignoring the less than helpful travel times, easing population pressure via interstellar immigration is a non-starter. Establishing a settlement is a tall order too. We don't even really know how to do this in low Earth orbit, on the Moon, or on Mars. We're a long, long way from being able to set up shop on an alien Earth, even if we could easily get to one. Regardless, what's important is that it may also help us answer the most fundamental question humans have ever had. How did we get here? For millennia, this question has inspired speculation, myth, religion, and philosophy. With a distant blue-white world hovering in the eyepiece, it becomes science. So, scientifically speaking, we look for other planets because we want to understand how they form. how conditions change their physical properties, and how they differ from or mirror the planets in our own solar system. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.